Welcome to another Foldit Lab Report. I am BKEP here at the Institute for Protein Design with my colleague Ian H. If this is your first time discovering Foldit Lab Reports, we produce these videos on the first of every month to tell you more about the science behind Foldit. This month, we are launching a new game mode for Foldit. DOJO Mode challenges you with a series of short exercises that range in difficulty from simple tutorials to rigorous tests of your folding skills. DOJO levels are adaptive. When you beat one, the next level will be easier or harder depending on your performance so far. The gameplay in DOJO Mode is also faster paced than in regular Foldit puzzles. There's a clock that's constantly ticking down. We hope that DOJO Mode will help bridge the gap between our simple tutorial puzzles and the heavy-duty science puzzles. And we especially recommend DOJO Mode for players who have maybe completed the tutorials but still find our science puzzles daunting. If you've ever opened a Foldit science puzzle and realized that you don't quite know where to start, DOJO Mode might be right for you. Veteran players might also enjoy honing their skills in the DOJO Mode. I want to give a big shout out to Foldit developer Josh, who is the mastermind and creator of Foldit DOJO Mode. So please drop into our Discord channel and share your feedback and suggestions on how to make DOJO Mode even better. Also new this month, we got lab results back for our MERS coronavirus binders. These binders come from a series of puzzles we ran in late 2020. Recall that MERS is a respiratory disease caused by a coronavirus, similar to COVID-19, which is caused by a coronavirus called SARS-CoV-2. To test for binding against the target protein on the MERS virus, we used the exact same experiment we used previously to test binders against the SARS-CoV-2 spike protein. In short, we insert custom DNA into yeast so that the yeast cells produce and display our binder designs on their surface. Each yeast cell makes just one of our proteins, but it will display many copies of that protein on its surface. When we mix these yeast cells with fluorescently tagged target, in this case, the MERS spike protein that's been engineered to glow, then the successful binders will stick to the glowing target. We can then sort out the yeast cells that are coated in fluorescent light. Lastly, we use DNA sequencing to match each successfully binding yeast cell with the protein design that it displays. Before we ran this experiment, we tried something new to boost our chances of success. Once we had identified about 60 promising Foldit designs, we recombined those designs with a set of protein scaffolds here at the IPD. This effectively increases the number of unique binders that we can test in the lab, giving us more shots on goal to find a well-behaved and successful binder. We amplified those initial 60 designs into a collection of almost 1,000 binders that we could test in this experiment. Long story short, we did not detect any successful binders in this experiment. Results from a parallel experiment, in which we're testing binders designed by scientists here at the IPD, suggest that this MERS spike target is more difficult than we thought it would be. The parallel experiment did give us some ideas about how we can improve Foldit binder design puzzles in the future. You should check out the blog for all the details about this. In our puzzle updates this month, we launched more protein binder design puzzles. These are puzzles where we want to design a protein that will stick to a target, like the MERS spike protein. In May, we ran binder design puzzles against influenza hemagglutinin, the TGF receptor, and Tie2 proteins. Please keep up the great work. We are seeing lots of very promising designs coming in, and we want to have as many designs as possible for lab testing. Also in May, we had a good old-fashioned structure prediction puzzle, this time for a protein found on the surface of Astrovirus. This kind of virus infects the digestive system of children and the elderly. By understanding more about the structure of Astrovirus proteins, we may discover ways to help prevent these kinds of infections. At the moment, scientists have collected data about this particular Astrovirus protein, but they haven't been able to turn that raw data into a 3D picture of how this protein actually looks. By taking on this structure prediction puzzle in Foldit, you might be able to generate the solution that unlocks this mystery. We also had some more symmetric design puzzles, where we are designing a protein that will assemble with other copies of itself. This included a special puzzle with D2 dihedral symmetry, or a dimer of dimers. This kind of dihedral symmetry is different from the cyclic symmetries that we're used to. and poses a new kind of challenge for symmetry aficionados. And that brings us to this month's design of the month. We have a binder design this month from Toshiue in puzzle 1985, TGF receptor binder design. This was the second round of our TGF receptor binder design puzzles, and we see a design here with two helices packed against the target protein and a beta sheet that's backing them up. So right off the bat, we see that this design has a strong core of orange hydrophobic residues and lots of blue hydrophilic residues on the surface. That's good. That means that this protein probably stands a good chance of folding up. If we look down here at the binder interface, we see that there are just two hydrophobic residues on the binder that make contact with the target. These two tyrosine residues, since that's all of the hydrophobic contacts, this may not lead to exceptionally tight binding. But what's very impressive about this design is that all of the polar residues at the interface seem to be satisfied. So let's see, if we look at hydrogen bonds, we see that all of these polar atoms on the target surface are being satisfied by hydrogen bonds made by the binder. And this is crucial. Even though this binder only has these two hydrophobic contacts against the target, I think this binder stands a pretty good chance of binding the target. And I will note that even though we only have these two residues, this tyrosine here is making very nice packing against the phenylalanine on the surface. The way that these two rings are stacked on top of each other makes very strong packing between those residues. So this is very nice to see. All in all, I think this looks like a very promising design. Again, please share your designs with scientists. We love to see what you are most interested in Foldit puzzles. And we are especially looking for more designs like this that have 100% satisfied interfaces with the target. That's all we have for this month. As always, thanks for watching, thanks for playing, and we'll see you next time.